Now let's talk about this. How do I store this runtime environment? So we know what to store, right? The question becomes, how am I going to store them, and how am I going to also retrieve them, right? So we use stack. Okay, so a stack area, okay, the caller or runtime environment and functions local variable are stored into a space in stack area known as a stack frame, or in a short is called a frame. So if you ever heard of this term frame in terms of high level programming concept, that's what we mean exactly here. Okay, that's what the mean by the frame. A frame is an area of the stack that is being used by the current function in question, or the current function in call that is using, which to use store all the local variables. Remember, like in the high level function, you can define local variable inside it. Those variables are stored inside the stack, and also any arguments also being passed on the stack. But by the way, they are not part of the frame. They are just part of the function call of the stack inside the stack. And also caller runtime environment is also stored inside the stack. So if we look at the frame of this is the, let's say this is the stack part of the memory. Okay, and you called a function with some argument, more than 4 arguments. Okay, so first part, you basically keep on pushing your arguments into the stack. We'll see an example in next lecture, how we are passing and retrieving those arguments. But let's, for time being, assume that we pass more than 4 arguments using the stack, right? So we keep on pushing those argument values into the stack and then call this function with using JL, jump and link. So then next part, okay, from the higher to lower, and higher part being pointed as a frame pointer register, FP register, that is the start of the frame of this instance of this function call. Okay, this instance of this function call, that is your start of that frame, is designated by $FP. That register stores that address, and then from that address and below, it is your caller runtime environment. Like let's say you know you are overwriting A0 and A2, you stored the value there. You're overwriting, let's say, S1 and S2, you're storing back there, and then you are, let's say you are also using S7 and S6, you stored them there, and so on and so forth. And then becomes your functions local variables. All of them are placed into this memory. Recall the high level variables are nothing but a name of an address, right? Integer A, integer B. That means you are referring to a piece of memory address, and if they are local in scope with respect to a function, those memories are allocated on the frame. Okay, so at the end of the frame, after the end of the frame, this is the blue area, let's say from a function call, from a theoretical perspective, then we have 2 word space after which your stack pointer is pointing to, means stack pointer address is pointing to a memory space in the stack region of the memory, which provides a double word push. Okay, just to accommodate in case you want to push double word into the current stack, so that it does not go and override into your function local variable that value. So we give a 2 word gap from the end of the frame. Okay, so in summary, your frame pointer is pointing to the start of your frame of a function, and initial region, it stores the caller runtime environment and then stores the function local variable. together caller, runtime, informant, function, local variable. That whole region is your frame for this instance of a function call. And then there is 2 word gap from the end of the stack frame, or a frame in short, and your stack pointer is pointing to such an address which allows a double word push. All right. Now let's look at this factorial example in the high level, recursive example, that how we can implement it at the low level. Okay. So this factorial, if you see, let's say we commented argument in A0. Okay, so we are passing the value to make a factorial of in the A0 register, and result is returned in V0. Okay, so that goes as a comment, and we start implementing that as a function, as a label. Okay, the name of the function is become a label if you want to kind of make a one-to-one correspondence with your high level code and to this assembly level. So your function name become a label in your implementation. Then you do the body of the procedure. Okay, so what basically it does, you are initializing T0 to 1, that register. So we don't want to make use of a saved register, S register, or anything $S star like S0 to S7. We don't want to use it absolutely if it is not necessary. Okay, but in this example I have shown you just to give you an example. I have used S0 in couple of places, right, just to show you an example. If you ever have to use an saved register, then you can save your runtime caller environment in certain way. Okay, some point why you need to do S0, you cannot avoid it even if you have like more than enough T register, because in your function, if you call another function, so another function is not honored to like store and restore back your temporary register, right, T registers. But if you need to preserve some value across the function call, you must use a saved register, because by the convention, if you call another function from your function implementation, then that called function is bound to restore your saved register if it uses it, right? So that's the reason why you may need to use a saved register. Okay. So anyway, let's get back to this procedure, what it does. First thing, initializing temporary register to 1, T0 to 1. Then it is checking like BLT, branch on less than. We are checking if A0 is less than T0. Means remember that if n less than 0, go to end of the factorial. That's my base case. So BLT A0 T0 to the factorial end. It goes there and place a return value 1 to the V0. Okay. And then we have something called factorial return. It's a good practice to like make an label called a return label, where we'll do some operations. We'll see it later, but at the end of the day, we'll do a jump register to $array. So that means jump back to the caller. Okay. So in this case, you start a function with a label, okay, and your body, and then it is a good practice to have your return part of the function code. It is not just a JR. We'll see, like of course your restore function, for example, will come into this place. So you label them as a end of that routine. So as a something like a factorial return in this case, you just choose a label of your own name. It's easy convention to have like an underscore RET as a name of the return part of the code as a convention. How do you label that instruction, start of that instruction, right? So It's a convention, so you can follow it, don't follow it is up to you, but I'd suggest, right, your function name is fact, your return code will be starting from a level called fact underscore RET, fact return. Okay, so BLT is my base case. I go to the factorial end, there I compute or preserve, like put the value in, base case value, and then I go into the factorial return as a normal follow through from that instruction. Then next is I move A0 to S0. I'm kind of preserving the A0 value so that I can make a A0 decrease A0 like n equal to n minus 1. I want to do that. Oh yeah, I have already said it. This is the base case, right? And let's see, now it calls itself. So we stored the value of A0 into S0 and we decrease the n conceptually. It's basically it was stored in A0, so we just make an A0 equals A0 minus 1. So that's what we did here, and we do a jump and link to the fact. Means at this point your control is now go over into the factorial and redo this whole thing again. Okay, so that means as long as I'm not hitting a base case, I'm just calling myself, right? Now as soon as I hit the base case, I return back, so my control will be transferred to this next instruction of the JL. This is mult. So here I am doing n multiplied by factorial n minus 1. So that means what? Like V0 contains a result from the previous from my call instance, and I'm multiplying that with the S0, the n I am storing, right? Remember at this point I'm storing S0 as my n of this step, these instances, right? And then I load the V0. Of course I have a limitation here. I'm assuming my factorial is result is bound within the 32 bit. I'm not taking care of the higher bit and so on and so forth. That's okay. Not very critical in this example. We're just trying to understand what the function call looks like, how to implement the function, and how to do the runtime environment storage and restore. Okay, so we are placing our multiplication result in V0, and now from here I am going to return of that factorial. So I'm kind of going over this base case return and jumping over to this and going straight to my return code from this function. So this is a conventional body of a function at the low level. Okay, and where should you implement it? You can start from the very beginning of dot text and start from that point and do all your function implementation part, and then goes to the main. Also main in this context is another level, right? Main, and then you do the main program code there. Or you can do the other way, like you have the main first, which has an exit at the end, and after that you basically implement your function. Like you start with the function label, name label, and then body, and then a return code. That becomes one isolated function, and then you go over, do another function. So one thing I have noticed that what students usually tend to do, mix of functions in between them, and they becomes like a spaghetti code, one implementation inside another implementation and so on and so forth, and they think that is a function. But be very careful about that kind of practice, because that will lead into usually a very, very tricky debugging situation. Okay, so keep the function implementation as content as possible. Like it is a self-contained code, piece of code, which will be exercised only if you call it using JAL. okay, JL jump and link to that level, okay, and think in that way, okay. So make always the function body self content, and don't mix up with function of another body, another implementation within that function's body, okay. So this is very weird practice. All right, so enough of that. So we come to the return, and then we implemented it. Now at this point, once your implementation is done, then you go back and review your code and determine what to be saved and what not to be saved, okay. So in this case, T0, okay, temporary register, no need to save. S0, yes, we need to save. A0 we are changing, so we need to save it. And of course JL save RA, because we are using JL. But again, as I said, as a convention, even if we are not calling another function or itself, it's a good practice, always save an array, okay. So it's a good practice. So now let's see a real-time example, right? For this call, what we need to do now, what we determined, we need to save S0, A0, array, and frame pointer, okay. So again, frame pointer is need to be saved because you are calling another function from itself, and that means that one call from the another call will create another separate frame, and your frame will be gone, frame pointer will be changed. So you must save the frame pointer. So if we are not calling another function, it's kind of okay to not store the frame pointer. Again, it is like an array register, that it's a good practice to have an FP stored as well, even if you are not calling another function. So in this class, assume that you are always, irrespective of whatever your implementation of the function, always store the frame pointer and array, okay. Now, so that means how many byte I need. Each register is 4 byte, so I need a 16 byte of total storage in the stack. So that's my frame size, okay. Frame size is number of variable into 4 bytes. And how many bytes I need to move the stack pointer. So remember, when we called at the beginning of the function call, when we jump and link into that function, our stack pointer was in the place of the frame pointer, means it was pointing to the place where the frame pointer is now pointing. Now stack pointer needs to move down by frame size and 4 bytes, not the 8 bytes. Remember, we want to leave an 8 byte storage, okay. Why? So that someone can do a push of double word, okay, into that. But again, remember, your stack pointer by our class convention is already pointing to a free 4 byte space, right? Our stack pointer in our class convention always points to a free position, 4 byte. So that's why we take account of that 4 byte, and our stack pointer movement size then become your frame size plus 8, like for this 8 double word storage space making, minus 4, because my stack pointer is already pointing to a free space. So that's my stack pointer move size. So our strategy would be, first, stack pointer is moved down to 20 bytes for this example. So 16 byte for the frame, and 8 minus 4, 4 byte plus on top of that is 20 bytes. So we first change the stack pointer value by moving it down, means you're subtracting 20 from it. Then we store S0, A0, array, and current frame pointer. In this case, what you can do, imagine as well, that instead of first changing the stack pointer, you remember we have a push operation, so you push FP, push array, push A0 and push S0. You can do that as well. Then you move the stack pointer by another 4 byte, right? Another 4 byte. That will also do. But the point there is that remember your push is always having a, what is this? This is a 2 basic instruction in your push macro, right? It is first, it is storing a word SW followed by subtraction of the stack pointer value, right? So for 4 push, you are doing 4 subtraction there. Store word is fine, but 4 subtraction there. In this way, if we move first the stack pointer down 20 bit and then store S0, A0, RA and AP current frame pointer value as with respect to stack pointer as a base and rest, okay, then we are avoiding this extra subtraction steps for the stack pointer. That means our runtime is like faster than what we could have done using our push macro. So that's why this approach, whatever approach I'm going to show you, should be the performance wise, it's an optimal solution, okay, not the push. So what we'll do here to store my runtime environment now, we first move the stack pointer by 20 byte, add I SP minus 20, then I do a store word with respect to stack pointer, current value of the stack pointer after it moves down as a base, and then add and 20 offset on that. So we are going to the top of the beginning of the frame. We store the frame pointer, then RA. So this is a good practice. Please follow this. First store the frame pointer, then RA, then you are kind of, if you have that practice, you can write the like store word, frame creation and deletion step like a breeze. Okay, so just follow this convention. So 20 offset from the stack pointer, store FP, 16 offset from the stack pointer, in this case store RA, and then 12 you store A0, you can alter these also, A0 and S0, doesn't matter. And then, so you store this 4 register, FP, RA, A0, S0, and then you set the frame pointer at the beginning of the frame by adding 20 on the current value of the stack pointer. So this is your runtime environment storing code. First, we move down the stack pointer by the move amount, and then we keep on storing those required register to be saved in the frame using stack pointer as my base register, and put the offsets with respect to that base registers, and then at the end we set the frame pointer value by adding the frame size, stack movement size. Like this is, if this is a minus 20, it becomes a 20 here. If this was, let's say, minus 40, it becomes a 40 here. So this is kind of become, if you understand the underlying concept, it becomes more mechanized step. You just move the frame pointer as a stack pointer plus whatever amount you move the stack pointer. Okay, so this is your runtime store code. Also, one point to note, just to check your storing is okay or not, that the last one, before you are setting the frame pointer, last one offset is always 8. Okay, however number of variable you stored there, if you store it correctly, write it correctly, you will see the last one will end up in a 8 offset from the stack pointer. So you are making a gap of 8 byte from the current stack pointer and the end of your frame. So this is what we are doing. We are moving the stack pointer, then storing them in the frame, and then end of the day we are setting the frame pointer. Your stack pointer was before the call, at pointing was this point. Now it is pointing at that point within the function. All right. Now one thing I'll probably show you in the Mars, that if you have this return RTE store code, then you can write the return code very easily. Okay, you just practically whatever you need to do, you copy the part from the store word to the add I. Okay, from first store word to the add I, change all the SW to LW, and here change the stack pointer. That's it. FP to SP. I'll show you. But anyway, let's take this example now. We just created a frame inside our code for the factorial. So what we have? We have RTE store code to start with. Then our implementation goes down to some part where we are calling this function itself, JL, and then rest of the implementations. Then I have some RTE restore code and JR back to the caller. Now let's say at this point your stack pointer value is SP0 and pointing to some free space in the stack. That's when we are calling this factorial. Let's say argument A0 is set as 5. All right. So what will happen first in the store code? Remember it was doing SP equals SP minus 20. So stack pointer moves to a new value as a SP1, and your frame is saved. Like your frame, inside frame, you have some value for FPX is, I don't know what the value of the frame pointer at this point. Whatever the value I'm storing there, I'm storing the return value of array, and I'm storing the value 5 for the A0 and some value of the X. I don't know what was the caller's value, but I'm storing it because I'm using them. So I am storing an X into the frame. So I'm not storing, by the way, like I'm just showing that A0 is 5, that being stored means I'm storing the value 5 in the frame for variable A0 to be restored. And I'm storing X for the variable S0 in the frame so that I can restore. So at this point, your frame pointer is now pointing, value is SP0. Remember to start at the beginning, I had SP0 equal to a stack pointer as SP0 value, some value, okay. Frame pointer should point to the same value, SP0, okay. So in the process, I first move the stack pointer, store it, and then adjust the frame pointer value so that it starts pointing to a place address with a SP0, some address. Then from here, from 5, it is not the base case. So I know this function will decrease the value of A0, set it A4 and call it itself. So at this point, what will happen, your stack pointer will be further shifted by 20 byte. Let's say it is SP2. And then you store your FP, which is current value is SP0. So that is being stored. Whatever array at this point, it will be stored. And A0 at this point is 4, it will be stored, and your S0 from the code, it was using a 5 value, so 5 will be stored in the frame. Now at this point then, FP, your frame pointer now switch to pointing to the SP1. Okay, that is start of this frame. So this is what I mean by instance of a calling. So first call from the caller, that instance of factorial calling creates this frame, first frame. Right? Then the first recursive step, that instance of the calling of the factorial routine creates this current frame. And at this point, now it is not base case, we decrease the value A0 to 3, call it again. So SP3 move SP, stack pointer move to SP3, 20 byte below. And then we create your frame pointer with the value SP1, which is the current value, right? Return address, whatever that address is, A0 is 3 and S is now in this case stored as a 4. And we move the stack frame pointer. Okay, this is not a base case. This routine goes over again. A02, we create another frame, and A01, we create another frame. And then A00, we create another frame. Okay, now at this point, it hits the base case, right? So as it hits the base case, what it need to do, it will just before return, pop your frame for this instance of the calling. this instance of the calling, it goes and pop the frame, okay, and return the value as a v0 to its caller instance. Now your caller instance is this point. Your caller instance has s0 value to 2, s0 1, its return address and some fp to sp3. It will multiply them, right? Your a0 is restored back, so a0 is 1, 1 multiplied by 1 is 1, so it returns from this point, pop the frame, return is v0 as 1, then multiply a0, you restore the a0 value, multiply it with 2, then you pop the frame, okay, that is restored the frame, right? Sorry, RTE store and RTE restored. That's what the pop the frame means, right? We kind of pushing the frames into the stacks and popping the frames from the stack. We're practically storing the RTE and restoring the RTE. So it returns 2, then a0 multiplied by 3, pop the frame, then v0 returned from that instance of the call as a 6, multiplied by 4, pop the frame, and return 24. Now at this instance of the call, which was originally called from the caller, right? 24, a05, multiply, pop the frame, stack pointer goes back to its place, and v0 is returned as 120. So that's how your factorial routine works.